Okay, here we are on part two. So now we're going to look at the slope and the end behavior of a linear function. Again, f of x equals ax plus b. Now the end behavior of a linear function is determined by the sign of the slope. So remember we had slope positive, slope negative, and so if we have a is positive, that means a positive slope, so we're going to have a line going up like this. Think about how that works. So it says our function is increasing, which makes sense because we have a positive slope. And so what are we thinking about? Well, what about the limit? So if we go to positive infinity for x, what's this output doing? Well, it's going up here to positive infinity as well. So the limit of f of x is equal to infinity when x goes to infinity. Now, when we go the other direction, we go to negative infinity. Well, what's this doing? Well, this is going down to negative infinity. So the limit of f of x as x approaches negative infinity is negative infinity. Now, what happens if we have that a is negative? Well, now we're kind of going the opposite direction. And so as we go, as x approaches positive infinity, that's going to give us a limit of negative infinity. So because it's decreasing. So the limit of f of x as x approaches infinity goes to negative infinity. And the limit as f of x goes to negative infinity is it goes to positive infinity for that. So the limit of f of x as x goes to negative infinity is positive infinity. Now we have this one, it's the constant function. So basically, we have this straight line, a horizontal line straight across. And that's when a is equal to 0. Now that gives us f of x is equal to b, so whatever your intercept is, it's going to be that same thing straight across the whole function. And the graph is that horizontal line. And so basically our limit of f of x as we go to positive or negative infinity, we just get b. So if we think about that as we go this way, no matter how far we go that way, it's going to be negative infinity, or it's going to be b. And as we go all the way to positive infinity, it's always going to be b. And so that one's one of those kind of really boring ones, but it's really nice to remember that when you have that constant function, you can go to plus and minus infinity and you get the y-intercept. Now the magnitude of the slope gives the relative steepness of the line. So, the larger the magnitude is, the more steep, the shallower it is, the less steep it is. Okay, now this is something, so this really ties into this note down here. And when you're looking at a graph and how steep a slope looks on the scale can be throwing you off, because two different graphs, will have sometimes different scales. Sometimes they're going to be, smaller or bigger, and so their slope will be looking different. And what could actually be the case is, one might be a lot greater than the other one, whereas they might actually be equal, or the other one might be steeper than the one that actually looks steeper. And so be wary when you're looking at graphs and try to determine, are they really comparable as far as the scale, everything, x, y's, both axes, are they the same measures? And, is it really the same slope? Now, a vertical line has undefined slope, and so it doesn't represent a function. So if you think about a vertical line test to be a function, well, a vertical line doesn't pass the vertical line test, and so that's not a function. So algebraically, basically, that just says x is equal to c, where x is the input variable and c is the constant, okay? But that's not truly a function, and so that has undefined slope. All right, so I think we have all the different kinds of lines we could make. And so let's start looking at some examples. So it says, is the outstanding consumer credit increasing, decreasing, or constant in this graph here? Well, here we got the consumer credit. Shows the outstanding consumer credit seasonally adjusted between 2004 and 2007. So as you can see, it looks like it's going up. So that means it's increasing. Okay, so we'll just circle increasing and we'll be done with that one. Now we're supposed to estimate the slope of the graph. Well, with slopes and trying to estimate from the graph, that's always tricky. So I'm just going to pick some points here. And that looks to me like that might be the point 2 comma 2400. Now 1 looks to be a little bit under. So maybe this point is 1 comma 2290. I don't know. We'll see what it is. And I don't know what it is. So, you could choose something there. Maybe you wanted to actually choose the intercept, but again, there it's even harder to do. Maybe that's a little bit more than the 90, so maybe this would be actually 0, and that would be 21, and maybe 85, something like that. I don't know. And so it's hard to choose what those points are when you're looking at just the graph and you don't have the data to actually pull the points out. So again, it doesn't matter which ones we use because we're just going to get a rough estimate of the slope. And so our slope A is equal to, maybe we'll do both of them. Maybe we'll do this one, we'll call, I don't know, let's call this one Y, or X1, Y1, and this one x2, y2, and this one kind of x2 sub 1 and x or y2 sub 1, just to see, how close estimates do they get. Are they close actually if we assume that those are the numbers? All right, so we'll do change in y over change in x. So we'll take, say, 2400 minus 2290 divided by 2 minus 1. Okay, so 2400 minus that 2290, that's going to give us about 110, I think. And so we have, that's, the slope is years per $1 billion. So it's going to, or I'm sorry, $1 billion per year, because it's the y over x. So billion per year. Okay, so that's roughly our guess with that one. And we'll call that with 0.1. Let's do 0.2. And so again, we're going to do 2400 minus, now we'll do 2185, and we'll do 2 minus 0. So 2400 minus 2185, that's going to be 215 over 2. So we divide that by 2, that's 107.5. If we put it into the same thing, it's going to be roughly 108 billion per year. Okay. So fairly close, not bad for guessing points on the graph. So either one of those I think would be a reasonable estimate. Now it says, and again, we're going to basically be the outstanding consumer debt. So we're increasing the consumer debt by, well, if we average those, 109 billion per year. So we're increasing the consumer debt by $109 billion per year on average. So we're going up by that much per year. Now it says give an estimate of U2. Well, we kind of used U2 as one of our points because we said 2 was equal to 2400. So that's equal to 2400, and that's dollars, and that's billions. And so that's going to be, the consumer debt in. And so we started at 2004, 2005, 2006. So it's in 2006. Okay, so you have to kind of remember what your units are. So this is years since 2004. So it's 2 years since 2004. So that gives us 2006. And these are in billions of dollars. All right. So that should give us that. And again, between the 2 points, averaging 109 billion per year, that's reasonable as far as using that as your slope. Okay, so a model. So it's an equation that describes the relationship between an output variable and an input variable, along with their defining statements. So we can completely define model. A completely defined model includes, well, we have to have an equation. So that's the algebraic representation of the function. We have to have a description of the output variable. And that's to indicate the nature of the output and how it is measured. And then we also need the same thing for the input variable, how to measure it and what is the nature of that input variable. And then we need a description of the input interval, okay? So indicating the interval of input values on which the model is based. So maybe, your model is based on 2 less than x less than, 2400, okay? So you have a long range. But what if you're say, oh, well, I want to look at something at 3000. well, is that actually in that interval? Not really. And so that's probably going to be a best guess. We're going to extrapolate the data and say, yeah, well, we'll assume it follows that same model past that so we can get that number, but we're skeptical if it really works. Now, if we had chosen a number in here, say x equals, I don't know, 1,000, then it fits that model because it's within that input interval. So that works really well. All right, so here we're looking at the resale value of a vehicle. So there was no good examples in actually the homework, and so this is kind of one in the book, so you'll probably have read it about it, but it's a good one to go through. So here we have the resale value of a used car is represented graphically in the figure below. So we've got the figure here. And what they want us to do is identify and interpret the point at which the input is 0. So the t is 0. Well, t is 0 gives that. So that point is 0, 12,000. Okay. And what does it mean? Well, at time equals 0, when you buy the car, basically, the resale value is $12,000. Okay, so that's what it means. Okay, and so that's resale value when you buy that used car. It's going to be $12,000. Now, identify and interpret the point at which the output is 0. Well, that's over here, and so that's going to be 8, 0. And here, this is a time equals 8 years after you bought it. There is no resale value. Okay. So you bought the used car, and when you first buy it, the resale value is $12,000. 8 years later, there is no resale value. Okay, so now we're supposed to calculate and interpret the slope of the graph. All right, well, we know how to do that. So we've got 2 points, so we could say, okay, well, let's take 12,000 minus 0 divided by 0 minus 8. And so that's going to be 12,000 divided by -8. And I'll just do that quickly on my calculator and I'll actually show you because I'm sure you can do that on your calculator. And so that's going to be negative 1,500. And what that is it's going to basically decrease in value $1,500 per year. Okay, so that's what's happening. We're decreasing by $1,500 per year. So we have a negative slope, and that's how we get it. Now it says write a linear model for the graph. Well, we've got the slope, that's our A. We've got the intercept, that's our B. So we can say, okay, well, let's say our resale value, R of X, is equal to, and now we'll have a negative 1,500 times X plus our intercept of 12,000. And so that would be our linear model for this item here. And if we plugged in 8 here, we're going to get 0. If we plugged in 0 here, we get 12,000. And we plug in any other number here, we'll get some point along this line here. All right, I'll pause there and come back in a bit.